Hello everyone, this is Ashaful. I'm going to present our work, a simple framework for cross-domain feature recognition with unlabeled data. I'm from Rensselaer Polytechnic Institute. This is a joint collaboration with my IBM intern mentors and my supervisor at RPI. Human can recognize an object by looking only at a few examples. However, modern deep neural network require thousands of examples per category to achieve the same human level recognition capability. To measure this capability, there has been this feature learning task. The aim of this task is to learn a particular instance or object by only looking at a few examples. For example, by looking at two examples per category in this figure. In a typical feature learning task, there is a support set which contains few example per category, and there is a query set. The goal is to learn the examples or categories from the support set and to evaluate it on the query set. And this same evaluation is repeated multiple times to get an average feature learning accuracy. Now, before the feature evaluation, there is this meta training phase where the model is trained on a large scale source dataset. And generally, this source dataset comes from similar domain as the target dataset. However, the classes might be different. And this setup actually limits the feature learning capability because as in real world setting, the source dataset can be from any domain. For example, the source dataset could be from ImageNet domain and the target dataset could be in a different domain like satellite images or medical images. To this end, cross-domain feature learning is a practical task where the source data comes from a different domain than the target data. For example, the source dataset can be supervised ImageNet dataset, and the target data can be from completely different domain like medical imaging dataset. It has been shown that simple transfer learning outperforms complicated meta-learning based feature learning method for both in-domain and cross-domain feature learning. Here we show a simple baseline. In this baseline, an encoder is first trained on the source dataset with supervised cross entropy loss. The encoder is used as a feature extractor during feature evaluation, and then a linear header is trained on top of the feature extractor from the support set and predicts the classes of the query set. This simple baseline is actually the state-of-the-art approach in cross-domain feature learning tasks. In our setting, we are also provided additional unlabeled dataset from the target domain. For example, let's say we want to perform feature learning on Euroset dataset, which is a satellite imagery dataset. We have labeled dataset of ImageNet and also lots of unlabeled dataset from Euroset. Our goal is to learn a good feature extractor for the feature task using the labeled source dataset and unlabeled target dataset. And we can learn this task in two different ways. We can either use the unlabeled source dataset and unlabeled target dataset during the meta training phase, or we can actually use the unlabeled target dataset during the learning the support set too. So in this work, we are actually focused on learning a good feature representation that is using this unlabeled target domain and labeled source domain during the meta training set. Using this unlabeled target domain during the feature evaluation phase is still remained as a feature extension of our work. This figure illustrates our approach. We have an encoder F theta and a classifier C which predicts the classes of the labeled source dataset. So the first loss function is vanilla supervised cross entropy loss on the source dataset, which is denoted here. We also use the unlabeled dataset for additional loss function. Specifically, given an unlabeled sample, we first create two augmentations, a weak augmentation and a strong augmentation. The weak augmented version is passed through the network to produce class scores. Now, although it looks like pseudo labeling, the class scores it predicts is actually is not the same classes as the original target dataset. Rather, the classes it predicts are projected to the source dataset. We then obtain scores for the strongly augmented version of the same image, and these two scores are compared to obtain unsupervised loss function. In essence, we are creating a consistency regularization loss. And this method can also be considered as well supervised losses like Biol and Dino, because in those losses we can also similar approach that two different that two different augmented versions are compared against each other to optimize the loss function. However, the big difference is that we are producing the final features from the classification layer for the source dataset. And we found that this simple solution actually provides pretty good results for the cross-domain future planning task. We perform experiments on the BSCD-FSL benchmark. This benchmark contains a source image, which is the mini ImageNet. A mini ImageNet is actually a small subset of ImageNet with 100 ImageNet classes. It has around 38,000 training images. And the featured data sets are Euroset, crop disease, chest X-ray, and ISIC. Here, crop disease is a data set of agricultural images, and it is the most similar to the ImageNet data set. Euroset is a satellite image data set with 10 classes. Both ISIC and chest X-ray contain medical images, which is completely different from the ImageNet kind of classes. So we train our model on the mini ImageNet dataset and also add additional unsupervised, unlabeled target samples, and then evaluate on the target dataset. Here we show the results of our approaches. For other baselines, we first show the performance of the meta learning method. The transfer learning baseline is actually the baseline with the cross entropy loss. Here, startup is a recent approach that uses the unlabeled data during training, and hence it is like most similar to our approach. We also show results for the SimCLR self-supervised models. So we can see that our method outperforms other methods in most cases. Especially for one-shot setting, the improvement is pretty significant. We get around 8 to 9% improvement in Euroset and crop disease dataset. We have also done several analyses in our paper. In this analysis, we experimented on the future performance for different amount of unlabeled data. As expected, more unlabeled data helps to learn better representation. Note that even with 10% of the unlabeled data, we can still get pretty reasonable accuracy, which denotes that even we have just a small amount of unlabeled data from the target domain, it can help to learn better representation which is suitable for the target domain. And one of the important aspects of better performance in cross-domain future planning tasks is the data augmentation, particularly in our setting. We have found that it is important to apply weak augmentation to create the pseudo scores and strong augmentation to the other one. The weak augmented version does not produce any gradient, so the gradient is passed through only the strongly augmented networks, and this can improve our accuracy a lot. For example, using just 2 weak augmentation on the 2 images and 1 weak augmentation and a strong augmentation for the 2 images have around 2%, more than 2% performance difference. So this implies that strong augmentation improves the accuracy, particularly in our setting. Another interesting question could be, does unlabeled data from different domain help? In this table, we see that this is not always the case. That is, the best accuracy is achieved when the unlabeled data and target data are from the same domain. Even if we add more unlabeled data from other domain, which is shown in the results in the final row, we can still see that it doesn't necessarily help. That is, unlabeled data from other domain can actually hurt the performance. So it's pretty important to have the unlabeled data only from the domain that we are interested in or we are going to evaluate on. Now, we have performed other ablation studies, and from those ablations, we found some interesting points. For example, we see that the labeled base dataset is still helpful, even if even if it's coming from a different domain. So our assumption is that it can provide a good initialization for our method to create the pseudo labels of the unlabeled dataset. We also found that it's important to apply stop gradient towards the weakly augmented version, and without the stop gradient, the accuracy decreases a bit. Here we show some T-SNE visualization of 10 classes from the crop disease and Euroset dataset. We compare the embedding extracted from the transfer, that is the vanilla cross entropy method, and our approach. We see that our method creates better grouping on the embeddings of the target dataset, even though we do not use any labels from the target dataset during pre-training. Uh, we found some limitation of our method. For example, it doesn't work so well for extremely different tasks, like for tasks that requires transferring from mini ImageNet to chest texture. It generally performs reasonably good in somewhat similar dataset or a dataset which is different, but there are some aspect of similarity. But the chest texture dataset is kind of completely different, and the representation learned from mini ImageNet might not always help in chest texture dataset. Another important aspect is that more unlabeled dataset helps, but it doesn't necessarily help too much. For example, using 10% unlabeled data versus 75% unlabeled data has only does only have around 2% or less than 2% performance improvement. So we expected to see more, but it shows that even with 10% unlabeled data, we can get pretty good and pretty reasonable performance improvement over the vanilla cross entropy model. So in summary, we introduced a new novel approach to utilize unlabeled data from the target domain for cross-domain feature learning. And we experimented, our experimentation shows that our method can achieve state-of-the-art results in the BFCD-FSL benchmark for both one-shot and five-shot classification. And the performance improvement for, particularly in one-shot classification, is pretty significant. Now, future work can focus on applying our approach in each task during meta testing, so that the model can learn more category-specific representation. So thanks a lot.